how the Yellowstone Hotspot shaped Oregon's landscapes, and a look at the Juneau Icefield Research Program from a PSU undergrad. Welcome to Geology Hour. I'm your co-host, Alyssa Smith.
I'm Carrie Gordon.
My name is Cameron Stallcup, and I'm a PSU undergrad student.
Hi, my name's Ellen Bishop, and I'm a geologist, writer, and photographer. I live in Halfway, Oregon, actually outside of downtown metropolitan Halfway, Oregon. And I'm here to acquaint you with the force that actually made most of Eastern Oregon and a lot of overall Oregon's landscapes tonight.
Well, hi everyone. Thanks for being interested in hearing me talk about my experience with the Juneau Icefield Research Program this summer as a student. And to start off, I wanted to show this beautiful picture looking across from JERP's Camp 10, looking across the Taku Glacier at the Taku Towers. And to start off with a brief introduction, I'm a senior undergraduate student at Portland State University. I'm a geology major, and I'm originally from Louisville, Kentucky. And I also wanted to start off with a sincere thank you to GSOC for helping me attend JERP. I really appreciate all the support. And I thought that I should also start off with what is the Juneau Icefield Research Program. So the Juneau Icefield Research Program, also known as JERP, to save some time saying it, is an 8-week field immersion on the Juneau Icefield. It helps students learn backcountry travel skills, glaciology, climate science, science communication, and gain skills pertaining to fieldwork. And JERP was founded in 1946 under the Foundation for Glacier and Environmental Research. And here on the right side, we have a picture of a mass balance pit where we dug down from the surface to last year's snow layer called the Firn, F-I-R-N. And at the top of it, we have a picture of all of us after we dug the pit, being very thankful that our 20 feet deep pit was done. And I think that I should also explain why did I want to attend JERP. My main motivations for attending JERP were that I've always been fascinated by changing landscapes. So some geomorphology and how drastically ice specifically transforms a landscape. And I thought that JERP seemed to be the perfect blend of geomorphology, glaciology, and climate change science, especially since they all intrinsically inform each other when you're studying one. And I've long wanted to gain some backcountry travel skills, so I thought that JERP would be the perfect opportunity to blend my academic journey with gaining some of these skills. And I was also super excited to connect with teaching faculty and some researchers and field staff to gain insights into the cryosphere research community, and also learn some more about like field science support roles and see where maybe could see myself fitting in the future. And so to start talking about JERP, the whole field season was separated by academic blocks. And so each block was about 2 weeks long. And so to start off with block 0, we started at Camp 30 in Atlin, British Columbia on June 14th. And Camp 30 is an old tuberculosis hospital that JERP bought from the town of Atlin. And most of the time there, we spent it getting acquainted with camp life and getting acquainted with our peers. We did a quick rundown of what the whole summer's traverse of the Juneau Icefield was going to look like. We also did a gear check with staff just to make sure that we had all the proper gear that we would need for this traverse, and taking note of certain things that we might need to pick up in Juneau before the actual traverse. And then we did a few warm-up hikes to practice hiking with our heavy packs. And this is where we also introduced our first academic topics. So some of those included an introduction to glaciology, science communication, radio comms, Earth's energy budget, wilderness medicine, how to balance your mental health in the field, and an introduction to glacial mass balance. And the picture behind the text, it's kind of hard to see with the text, but it's a group of students hiking down from Monarch Mountain, or in local Tlingit language, it was known as Ahika Day. And then on the right-hand side is a view of my sleeping setup one of the nights. We tried to sleep outside as much as possible when it wasn't raining or too cold. And so we just slept outside the dock overlooking Atlin Lake, and it was insanely gorgeous, as you can imagine. And to give a quick overview of the ski traverse, it totaled to about 79 miles. And I thought that this map was a really helpful way of kind of putting into perspective how we started in Juneau and then we ended the traverse on, at least the traverse on our own 2 feet at the Atlin Lake / Llewellyn Inlet campsite. And so I just thought this really helped put into scale of we put some miles on our skis that trip. First, we had to get from the town of Atlin to Juneau, Alaska. So we left Atlin on a charter bus, which was a 4-hour drive to Skagway, Alaska, where then we caught a 6-hour ferry ride to Juneau. And on the ferry ride, we had our first reading group discussion with Dr. Aaron Chesler discussing iron cycling from glaciers to the oceans in Southeast Alaska. And then while in Juneau, we got settled in the University of Alaska Southeast dorms for a couple days while we ran some last minute errands and got some last minute gear. Like I had to grab a sleeping bag liner because I was scared I was going to be cold. And then the top right picture is a picture from the ferry ride. The bottom right is a picture also from the ferry ride, but of one of the reading group discussions. And then the picture of the bear is just a picture of a bear as seen from the charter bus. The bus driver was nice enough to like pull over on the side of the road so we could all ooh and awe at the bear. And starting with our first traverse. So that was Blackerby Ridge to Camp 17. And this one was pretty darn steep. So once we hiked up through the forest and reached above the tree line, it was pretty much whiteout conditions the rest of the day. It was lots of boot packing in snow and kicking in some steps for all the people behind us and all the trail parties that would come up later that day or the day after us. And we pace ourselves by taking a 5-minute break every hour of moving with about a 10-minute lunch break. It was pretty cold and windy, so we didn't really want to stay that still, but it was pretty cool on the hike up. We got to discuss all the changes in rocks and see all the like beautiful metamorphic folding and all of the foliated like tonalite rocks. It was pretty amazing. And then the bottom right picture is a picture of the cook shack at this camp. And as most of the JERP buildings go, it's a wooden structure kind of covered in some like aluminum siding to help protect it from all the harsh winters up there. And while we were at Camp 17, that began our block 1. So the academics covered in block 1 was glacial hydrology. So how the water moves under the glacier, in the glacier, and on top of the glacier. We also talked about numerical modeling of the glacial hydrology, microbiology in harsh environments, and radio comms. And we focused heavily on developing some of our field skills during this block. So we learned a lot about rope systems, tying knots, how to self-arrest, some good ski practice, how to rescue someone if they fall in a crevasse, traveling on a rope team, on skis or just walking in the snow, how to take care of blisters or hypothermia, and then general glacial safety and glacial hazards that we might encounter on the traverse. And so the top left picture was our first like helicopter resupply, which is really exciting. It was all like, ooh, this feels like a crazy adventure. There's a helicopter resupplying us. That was insane. And then the bottom left picture is all of our skis set up. And then the middle 2 pictures are pictures of the inside of the cook shack when we first got there. So it was pretty like not set up. We were the first group there, so we got to set it up for everyone else. And then the picture behind the text, it's a little hard to see, but above and below the field skills paragraph, see there's a helicopter that's carrying a sling load just below the glacial safety and hazards. That was some gear that they ended up dropping off for us. And our first ski traverse of the trip was a 2-day ski traverse. It went from Camp 17 to an intermediate snow camp just above the Norris Icefall, which we called the Norris Cache. And in my opinion, this felt like the hardest day of the whole trip. I'd probably skied 5 times before the trip, and this was a lot of skiing, lots of elevation gain and loss. We started at about like 4:30 in the morning, and then we got there just before dinner time, so we got there around like 6:45 p.m. And we took a little breaks when we needed it, but we finally made it to camp just before the sun was setting. So the bottom right picture shows our tent camp set up in the snow with all of our sharps, our skis, ice axes, and ski poles on one side of the camp. And then the top right picture was the view from camp, just overlooking the other mountains. And it was pretty bad weather before this day. So we were very lucky that we could actually see things and it wasn't raining on us. So that was wonderful. And then we woke up in the morning just to do it all over again. And the next picture is a very realistic picture of me on the ground, as it happened a lot since I was learning how to ski. But you can see behind us is the Norris Icefall. And then on the left side of it, there's a little snowy slope, and that was where we skied up attached on a rope team, zigzagging around some crevasses. And this is my trail party leader, Riley, asking me once again if I needed help standing back up. But it's okay. I ended up getting it pretty fine towards the end of the trip. And so the next day looked like this all day long, the entire about 13 miles. So this was from Norris Cache to Camp 10. It was pretty flat, cross-country skiing all day, whiteout conditions, but it wasn't bad. We played little games in our heads and just talked, and we talked about all the fresh food that we couldn't wait to eat once we got home. And then once we made it to Camp 10, that was when block 2 started. And so our block 2 academics, we went pretty heavy on the academics here. So we talked about like fluid mechanics, snow, firn, ice transitions, and how that transitions to glacial ice, and then geomorphology and glacial isostatic rebound, environmental policy and strategy, the history of environmental regulation, some large-scale glacial dynamics, ice physics, some ground penetrating radar, also known as wide angle reflection and refraction surveys, paleoclimate and ice coring, and a couple drone LiDAR surveys. And so in the top right picture, we were collecting some snow surface samples. And then the bottom right picture was after a really long day of ski towing, so being pulled by a rope attached to a snow machine, just so that we could go a little bit further and quicker that day. And it was pretty rough on the knees, so we were really excited to just fully extend our legs for a moment. So on our breaks, we would just like stick our skis into the snow and lay down, and it felt great. And then after Camp 10, oh wait, before I get to that, these are pictures from an overnight trip we did while we were at Camp 10. We went up to the divide between the Llewellyn, Mathis, and the Tulsaquaw glaciers, and we did some ice coring, and we drilled 19.19 meters deep into the glacier so that we could analyze these for stable isotopes, which would inform paleoclimate studies. And they were sent back with a researcher at the University of Colorado Boulder. And then after Camp 10, we had our traverse to Camp 18. I think this felt like the easiest traverse of the day, although my feet and blisters might disagree. But the weather was great. It wasn't too sunny, not too hot. We had some nice katabatic winds. This is a silly picture of me eating a snack, and I was listening to music for part of it, eating my little fruit snacks to get my sugar in for the trip. But it was nice, like gentle uphill, and then we kind of got up to like a little ridge, and then this was the only one that you like skied down into the actual camp, and that was always fun. It was like a nice little bunny slope, which was Cameron friendly. And then while we were at Camp 18, we made it just in time for the sunset. So on the left side of the screen is a picture of the Von Lewis icefall, and I just thought that was like beautiful, seeing how all the ice is starting to fracture and fall apart as it's about to move off this cliff and through the canyon. And then on the right hand side is a picture from my sleeping bag. We decided to sleep outside that night because it was just such wonderful weather and probably like 50 degrees, so it was pretty pleasant. And then at Camp 18, that was when our Block 3 academic started. So we talked about glacial grounding lines, glaciers and watersheds, art and science, incorporating indigenous knowledge, ice-ocean interactions, temperature lapse rates, ice fabric and crystals. And then we also had a student group like mini research project, which I'll talk about on the next slide. And in this picture on the right-hand side, there's a picture of me. I'm in the orange, rappelling down the mass balance pit where we take samples every 10 centimeters on the south facing wall. And knowing the volume of the cylindrical tool that I'm using, also known as a jacket ripper, because it has some nice sharp teeth on one side, then I would take my sample and pass it up to some fellow students that would then weigh it. And then knowing the volume and the mass, we could calculate the density of the snow every 10 centimeters down to the last year's layer of snow, the firn. And to talk about my student group mini research project, we tried to study the formation of ogives. And I didn't know what ogives were before I attended JERP, had no clue at all. But if you look at the picture on the right-hand side, you can see those arc-shaped bands of alternating light and dark ice. And those are exactly what ogives are, all of these arc-shaped bands of the light and dark ice. And so we wanted to understand why do ogives form, because their formation processes are still unknown. So there's three leading hypotheses, but we wanted to explore one of them, which was, are there seasonal velocity variations that's creating like a stretching and compressing of the ice beneath the icefall? And so our main research question was, were there daily fluctuations in icefall velocity that could be a possible contributor to ogive formation? We're also limited on time. We only had about 5 days to do this little project. So our instruments that we used were tiltmeters, seismometers, and GPS devices known as MLIDs. But the project kind of just turned into like a lesson learned of, if you complete 10 or 20% of your fieldwork objectives, that is still a success. I'd say we probably completed 5% of it. The weather just didn't really cooperate, so we couldn't put our sensors where we wanted to. And we had trouble getting some of the data off of, especially our seismometers. But it's a good lesson learned, and science takes small incremental steps towards a goal. And we have lots of recommendations for future research studying ogives. So lesson learned. And here's a picture of our research group overlooking the Gilkey Trench with one of my favorite outhouses on the ice field called Big Bird. Going from Camp 18 to Camp 26, that was traverse number 4. It was our last traverse skiing. So we skied off the snow onto the blue ice of the ablation zone. And from there, we just had our microspikes on. And I think the picture on the right really puts into perspective the scale of the glaciers. You can just barely see some little students walking down here, and then just the whole width of it is all the Llewellyn Glacier. But I thought that picture was pretty cool to see. And at Block 4, that was we stayed at Camp 26, where that was probably the smallest camp on the ice field that everyone stayed at. And the academics that we talked about were remote sensing, science communication, dendrochronology, some more glacial hydrology, and we covered our final exam. And so the middle picture that's all sunny is of Camp 26. I just thought it was nice that we actually got some like good sun. So that was a beautiful picture and a good feeling. And then the picture on the right is one of the ice caves that we were able to explore from Camp 26. And leaving Camp 26, we hiked off of the ice field completely. So it was lots of zigzagging around crevasses and hopping over them. And then we hiked off of the Llewellyn Glacier to into Atlin Lake, where we would camp there that night and then be picked up in the morning. And so the picture behind the text is the terminus of the Llewellyn Glacier. In the middle is some students jumping over some crevasses with their microspikes on. And then the top right was the last time that we would be on the ice field this summer. So we hopped off the ice field through this little notch in the rocks, and it was the last time that we would see the ice. And then this picture on the bottom right was of me with the ice field tucked away in the mountains behind us. And the sole of my shoe decided to just completely come off on that hike. So we like duct taped it back on. And so you can see the little like white duct tape on my shoe at the bottom. That was pretty funny. I was just thankful it made it to the last traverse. And then at the inlet, we camped there overnight. And in the morning, a local from the town of Atlin named Archie, you can see him here in his boat, He would pick us up in groups, and he drove us back 2 hours to the town of Atlin, where we were greeted and reunited with the Jerp Lake town staff. And one expected or unexpected outcome of this trip was the community aspect of it. I thought I hadn't really considered that when applying to JERT, but it was really incredible. So I wanted to just show a couple pictures that encapsulated some of that community aspect. So here's a big group picture with all of us. Here I am down here. And next, this was our first 2-day ski traverse with some friends. And we were practicing our skiing downhill a little bit, being roped up. These are some other students eating dinner at Camp 10. I also had my birthday on the ice field, and so some students decided to bake me a little pan of brownies and give me a card, and I just thought that was really sweet, so I wanted to take this picture to capture that. And then once everyone would get off the boat in Atlin to be back at where we started at Camp 30, they gave us all a slice of watermelon because we were all so excited to just like, eat something fresh. And so in this picture, you can see like people are just excited to be like eating their little slice of watermelon. And then some more friends at Camp 10 overlooking the Taku Glacier and the Taku Towers. This was the group that I got to explore some ice caves with. That was pretty spectacular. This was my last trail party group as we hiked off the ice field. And this is my little bunkhouse at Camp 10 called the Pullman. And I stayed in there with 3 other guys. So we just wanted to take a picture to remember it. And then some students on the ferry ride from Skagway to Juneau. And last but not least, it's just a picture of some students as we're walking down to get onto the ferry. But I just thought the little archway made some nice framing. And last but not least, I wanted to end with this beautiful picture of the Von Lewis Icefall and a sincere thank you all for listening.
Oh my gosh, Cameron, what an adventure. So we have time for a few questions, and we definitely got some questions. Starting off on that Traverse 1, you encountered whiteout conditions. How can you be certain that you were still on the trail? And is the itinerary one that remains the same year after year with familiar guides? And does Gary asking a lot of questions. Did GPS play a role, and what safety systems do you have for contacting first responders for medical evac, like voice satellite phones? You know, and those are, that's both running from the safety to how in the heck did you not get lost in that whiteout?
All very valid questions. So I guess I'll try to go in order of those. A lot of the field staff, so there was 6 field staff that would be in charge of the groups of students. And so they would all have GPS devices, little like Garmin's, and then they also had like Garmin inReaches that they could text from, or like at least connect their phone to and send a satellite message to and from. But then on their phones, there's like a shared JERP CalTopo map. And honestly, that was very accurate. They allowed us to also download it, and then we could look at it on our phones and look which direction we're going. And then you could also like see how far you are. And that was really helpful, in my opinion. Some people didn't like to know how far we were, but I loved it.
This, especially in this day and age, how is this program funded, and is it reliant on federal grants?
This one is not reliant on federal grants. Most of it is funded by the student field fees, which is quite the financial barrier to access. They offer some financial aid, but you can also defer your enrollment for a year while you try to find some more aid or funding resources. But they're also pretty good at like helping you brainstorm ideas and reaching out to people, and like they could even help like provide like just helpful like letters to people that might be like skeptical of like, well, why do you really need to do this? Or they're really helpful at like helping you connect you with resources as well. I think this past year they did get some federal grants trying to do like, what was it? They're trying to archive a lot of the literature that is located up on the ice field, but in like only on the ice field, just at the JERP camp. So I know they got a pretty good grant to help them do that. And then I think there's some other researchers that have possibly gotten some grants to help do like research on the ice field, which is one that I was really lucky and grateful to be a part of, was like studying the impacts of like rockfall in the Gilkey Trench. So that was exciting.
Were there any Indigenous students in your group cadre?
Yes, there's one Indigenous student, and she was from Anchorage, and she had also like participated in the Youth Native American Olympics, and so she was like showing us some of the games and stuff that they competed in, and that was really exciting. And JERP also emphasizes a lot of like incorporating Indigenous knowledge, and so we were able to have someone from the local Tlingit community come up on the ice field this summer, and her name was Barb Dawson, and she was incredible just to like learn from her, and she also learned from us. And as like a thank you, she brought up some salmon to the ice field, so we got to like cook this delicious salmon dinner. It was scrumptious.
Oh, I bet it was. That's wonderful. So, and I don't know if folks caught this, but there was a question of what time of year was this, and your mom answered that it was what, June, middle of June through the middle of August. So you just recently,
Yep.
you're just off the ice, so to speak.
Yep. Just in time to freeze up again.
Of the research group that set out on this trip, how many members survived? Did
Luckily,
everybody
all of
make it
us.
from
We
A to
all sure
B?
did. We sure did. There was a couple minor injuries, just some like knee injuries, as can happen pretty easily with skiing. But everybody was expected to make a full recovery, and everybody met us at the very end. So it was pretty good.
Well, that's wonderful. What was the application process for this program? Were there mandatory alpine requirements? How were the candidates who were not physically capable of this trek eliminated? Because I'm
Mhm.
looking at that going, my, that is one athletic field camp, big time. Huh, Alyssa?
Yeah, that's my field camp experience was pretty strenuous, and this blows that out of the water. So that's pretty wild.
I definitely struggled sometimes, that's for sure. I'm not exactly sure how they eliminated people that like wouldn't be able to complete this, but also so the application process is quite a few application questions, and then you also submit like your transcript, and the whole thing is like no experience necessary. So I really took them up on that, and I was like, okay, they wouldn't say this if they didn't mean it. And then I just made sure I knew that it was going to be like physically intensive, so I made sure to like properly train for it. I started going to the gym and just walking up and down the stairs at Mount Tabor here in Portland. Um, and I was really glad I did that, because there's definitely some days where I was like, oh my gosh, I don't know if I'm gonna make it. But I did. Everything was fine.
I know that feeling. Cameron, what a delightful presentation and what an amazing field camp. That was wow. I think, man, kudos. That was wonderful presentation. And boy, did that make me think back
Thank you
to
so much.
how much you learned in just a few short weeks.
Oh yes. Well, thank you.
Well, I think we're right at the time to move on for our next presentation, and I am so pleased to be able to introduce you to Ellen Morris Bishop. And I'm so looking forward to learning about how the Yellowstone hotspot crafted our landscapes. Ellen, please take it away.
So this is kind of a story of how Yellowstone went from being just a place off in the middle of, or the corner of Wyoming, to being a place that basically is a very important spot for the Pacific Northwest. So when we say Yellowstone, most of us think about this, geysers and hot springs and maybe a caldera as well. So here's a generalized map of Yellowstone. And when I talk to people in Eastern Oregon, and say, well, we're I'm going to give a talk about Yellowstone, they usually expect that I'm going to be talking about Old Faithful and other things. But the Yellowstone hotspot has been a actually a very recently discovered feature of Northeast Oregon, and in fact the whole Pacific Northwest's biography. So let's kind of dive into this. When we look at the entire products of the Yellowstone hotspot, and I say that basically it's, something it's crafted most of, or a large part of our geology. This is a map of what we now are pretty well convinced is are the products of the Yellowstone hotspot in Oregon. And there's also a lot of effects in Washington that we'll take a look at as well. So we'll just kind of dive into this. And one of the things that I want to look at is the fact that Yellowstone hotspot idea is actually, I think, the rise of kind of a new paradigm in how we understand Pacific Northwest geology, particularly that of Washington and Oregon. A paradigm is a philosophical and theoretical framework of a scientific discipline within which theories, laws, generalizations, and experiments in support of them are formulated. In other words, a paradigm like plate tectonics today is something that we have as a framework for how we understand geology and how we understand the world around us. And so that's an important thing to keep in mind when we're talking about geology, because the rise of a new paradigm or a new way of looking at the world, looking at your discipline, looking at how the world around you formed, first of all, requires imagination and vision. And then it kind of transforms our understanding and imagination of how the world around us formed. So I want to talk really briefly about sort of how our understanding of Yellowstone has evolved over the last 120, 130 years. The first geologist who, I'm not going to talk about indigenous experiences there because they are many and deep and go back for probably 16,000 to 18,000 years. But the first geologist who got to Yellowstone in 1871, Frederick Holmes, made a map and observed that geologists have but glanced at the surface features of the country, and that the more profound and intricate problems remain almost untouched. And he was more than correct. So the first thing that Holmes did was make actually a map that was an extraordinarily good map, not only for that time, but it's still accurate today. In the 1950s and 60s, a geologist named John Boyd mapped rhyolites and tuffs, but he didn't think that there was, he just said, well, this is a rhyolite and this is a tuff. He didn't connect that with explosive volcanism. That really didn't happen until the 1960s. And so it wasn't until the 1960s that we began to realize that Yellowstone was more than a place that just puffed out a little ash every once in a while, that it had a very dynamic and explosive geologic history. Now we're going to whip over to the other end of this. We're going to go to the Oregon coast. And in 1968, Parks Snavely recognized that Eocene coastal basalts were alkalic, and he suggested a Hawaii-like source. But in 1968, a lot of people didn't think plate tectonics were worth much and didn't, it was kind of a weird thing and hadn't actually been kind of formulated into any coherent theory. And so basically his conclusion was that the coastal basalts, Eocene coastal basalts in Oregon, were erupted on the Oregon coast into a eugeosyncline. And some of us will remember what a eugeosyncline is, and others will be left completely in the dark. And I'm not going to explain that at this point, but it's the theory that preceded plate tectonics. And then finally, in 1972, Jason Morgan, is part of the plate tectonic revolution, wrote a classic paper on mantle convection. And he noted that there were mantle plumes, which was a whole new concept. And he pointed out all the mantle plumes in the ocean, Iceland, for example, and Hawaii. He never mentioned any mantle plumes on land, but he did, on his map, have Yellowstone shown as a mantle plume. So that's the first time that Yellowstone actually appeared as a mantle plume on a map. And not everyone believed that it was a mantle plume, and there are some skeptics yet. 1979, you'll see the relevance of this quote in a bit. Don Swanson defined the Columbia River basalts as the Columbia River Basalt Group, but he excluded, quote, all significant sedimentary interbeds between basalt flows from the Columbia River Basalt Group, and that would be excluding all the tuffs, anything that might have had layering in it. And ultimately, it's excluded any rhyolitic rocks from this Columbia River Basalt Group. We're going to see that those rhyolitic rocks, as Carrie well knows, are extremely important to the story of Yellowstone and how it defined our landscape. Finally, in 1982, Bob Duncan at Oregon State University recognized, quote, a captured island chain in the Oregon and Washington coast ranges. And he basically was the first person to say, well, maybe this is not only volcanism on the coast, but if it's a hotspot, if it's like Hawaii, and Bob Duncan was an oceanographer, is an oceanographer, who studied Hawaii. Maybe if it's a stationary plume, maybe North America moved over it. And maybe the Columbia River basalts might possibly have been a product of this plume. And maybe the basalts of the Snake River Plain might be there too. Notice he's talking about basalts, basalts, basalts. And his student, Doug Pyle, was an office mate of mine at Oregon State University. And Doug and I had, this is in about 1980, before Bob published his paper. So Doug and I would have lots of conversations about the idea, and this is where the imagination and the vision of the larger picture and trying to take things that don't make any sense at the moment and put them together into a new model comes in. Doug basically was convinced that he'd studied the basalts at Roseburg, and he was really the one who defined that these were alkalic basalts and were seamount basalts for the Oregon Coast Range. And so Doug was of the mind that if this was a hotspot like Hawaii, that North America would have moved over it. And he looked at the age of, let's say Smith rocks, and said, well, that's actually about 25 or 30 million years old. And if the plate was moving at this rate, then the hotspot would have been underneath the Smith rocks at that time. And at the time, we had no idea what the hotspot track actually was, but that was his idea that, that Smith rocks would have possibly been part of the emanations of the hotspot, or at least produced by the hotspot. And that if you go a little further, you get to the Columbia River basalts, and you get to the Strawberry Mountains, and you get to the Oahes, and then you sort of start going up the Snake River Plain. But nobody believed Doug at that time, at least certainly not for something like Smith rocks and all of the Columbia River basalts. Bob Duncan his advisor finally came out and said, well, yeah, it could be the Columbia River basalts, but we're not entirely sure. So then things begin to shape up. We begin to develop a paradigm that the Yellowstone hotspot basically is producing at least the rocks along the Snake River Plain as a hotspot as North America moves over it. But in 1992, the primary idea of most geologists was that the Yellowstone hotspot first reached the surface at McDermott Caldera in Southeast Oregon. This is diametrically opposed to the Duncan model, where it's a 50-year-old or 56-million-year-old hotspot that all of North America moves over. Then Vic Camp in 1995, actually, again, it was another geologist who came out and said it's responsible for the Columbia River basalts. The hotspot track began as CRB eruptions waned and North America moved west. So he's not connecting this with the coastal basalts and the Silesia basalts. Now, all of a sudden, now you're going to see that we can blame the Yellowstone hotspot for other things besides just basalts. So in 2004, it was fingered for producing high lava plains volcanics. In 2014, we finally get to a geologic history of Silesia, as the Silesia plume becomes is then fingered as the Yellowstone plume in 2015. Now it's the trigger for basin and range expansion. So suddenly this whole idea of a Yellowstone plume is not just a simple little plume, but we're going to see that it's a plume that comes up underneath the North America, spreads out, and does just amazing things. So some of this is still controversial, whether or not it triggered basin and range expansion, how responsible it is for the high-level plains volcanics. But in 2017, Camp and Wells basically came up with a very comprehensive paper on the idea that the hotspot goes all the way from the coast, or at least the trace of the hotspot goes all the way from the coast to Yellowstone National Park. And now people are beginning to look at the effects of the hotspot around Yellowstone and on into Wyoming, where the continent is beginning to move further west from the hotspot trace. Now, finally, we get to the rhyolites, which were very badly discriminated against by Don Swanson. And the irony is that this Streck Ferns et al. Paper appeared in a GSA paper that was dedicated to the, or GSA special paper that was dedicated to the contributions of Don Swanson to geology, even though Don Swanson had said, no tuffs, nothing that's, light colored, can't be in the basalts. And then finally, now we have Martin Streck at Portland State declaring that there's such a thing as the Columbia River rhyolites. So now we have the Columbia River rhyolites and the Columbia River basalts, which makes perfect sense because if you look at the rocks along the Snake River Plain, that's what you have. So this is basically from Vic Camp's 2017 paper, and it basically shows a nice illustration of basically the progression of the Yellowstone hotspot as North America moves over it. You'll see that the little red dots there give you the location of the hotspot all the way from 40 million years, and actually it's 50 million years when it collides with the coast, up to where it is today in Yellowstone. So you can see this plume of magma, first of all, comes up right under the coast at 40 million years. It produces the Tillamook volcanics because it's able to kind of get through the Farallon plate that is actually blocking it from getting all the way to the top. And so we have a really spotty occurrence of the Tillamook volcanics, somewhere they're between about 45 to 38 million years old. They're on the coast, and the next slide will show you what that looks like. And then it goes, this plume has to go underneath the early Cascades arc. There are a couple of small calderas in the Cascades that have been alluded to in the Western Cascades, have been alluded to as actually produced by Yellowstone, but that's controversial. And then basically it goes the North America continues to move west. So by about 30 million years, it's pretty much under where we would say Smith Rock might be today, which is really perfect timing because Smith Rock is a caldera. It's part of the Crooked River caldera, and Carrie can tell you all about that because she did a lot of work on that. So Carrie and Mark Burns and Jason McClarty just sort of defined that. And then basically the continent continues to move so that by 20 million years, the hotspot is kind of under Southeast Oregon, and it's beginning to produce two things. It's beginning to produce Columbia River basalts, but that's not until about 17 million years. So the first thing that has to happen is that hotspot the plume has to manage to burn its way through the overlying Farallon plate, which you can see in Vic's diagram there. And so when we look at the Steens basalts, for example, what we see under the Steens basalts are a 20 million year old rhyolitic magmas or lavas and tuffs, mercury deposits, things that look a lot like some of the things we find in the Owahis, where, near Smith Rock, where the plume had actually done kind of the same thing. So it melts part of the crust. The crust basically then can erupt as a caldera, and then you end up with basalts coming out after that. And then finally we get to the edge of the continent, and we end up with other things. So these are kind of my simplified cartoons with the Siletzia mantle plume off the coast, the Farallon plate heading towards the accreted terrains, North America moving to the west. And this is basically what this looks like today. We have, this is Cape Perpetua and the Ahats basalts. They are around 50 million years old, and they are some of the material, the basalts that were erupted onto the North American continent that Parks Navely considered being erupted basically into a eugeosyncline from a stationary source. It was a stationary source, but North America was moving to the west. Okay, so these are pillow lavas on Mary's Peak that are part of the accreted Siletzia terrain. We'll show you the extent of Siletzia in a minute. There's another pillow lava. And these are Gray's Harbor basalts that were actually erupted at about 45 million years into obviously a wet coastal environment, but erupted onto North America. So then we're going to have the Yellowstone hotspot kind of push its way through the old Farallon plate. It's actually going to melt some of the old Farallon plate. It's going to actually produce some rocks that are very high in potassium, very silicic rocks, and those will include the andesites and dacites of the Strawberry Mountains, as well as the rhyolites of Dooley Mountain and other things. So we're going to back up basically to pretty much the 25 or to 20 million year old location here, and we're going to take a look at okay, we're going to take a look at what happens when the Farallon plate, so we have, this is about 45 million years to 30 million years. So we have the Farallon plate. Here's Siletzia over on the left-hand side. And you can see that the large blue dots are Tillamook volcanic sites. The kind of blue-gray is the extent of Siletzia, the accreted terrain that goes under the Willamette Valley. This is basically as the Farallon plate hasn't been breached by the hotspot quite yet. And if you look up in Washington, you'll see that you have a couple of things going on. There's basically a couple of the Swauk and Chuckanut basins in Washington are actually one single large basin. It's kind of a large dent in the Washington, in Western Washington. made by the collision of Silesia. Then you have a couple of gneisses and also granitic rocks formed in the western, in the North Cascades here. Then you have the Kettle Dome, the Okanagan Dome, and the Colville batholith in here. You have the Republic Graben. So a lot of the geography in northern Washington is formulated by the passage of not just the hotspot, but also the plate that went along with the hotspot, the Farallon plate underneath Washington. So about the same time and a little later, we have Smith Rocks. We also have the Tower Mountain caldera. We have the Wildcat Mountain caldera that may be Clarno, but Clarno may also have been affected by the Yellowstone hotspot. At least that's what Jason McClary was talking about yesterday when I was talking with him. So we have large expanses of the John Day Formation, and we have basically the Crooked River caldera erupting. Here's Smith Rock. And the Crooked River caldera, 29 to 30 miles wide, Carrie? Yeah, about 30 miles wide. It's almost the same size as the Yellowstone caldera, erupting at essentially 28 to 30 million years ago in multiple eruptions. So that actually produced much of the ash that we find in the Painted Hills, and there are probably other calderas of similar ages. Some of them may actually be in the Warm Springs area. Some of them may be buried by Columbia River basalts. But if you look at Carroll Rim in the Painted Hills, it's the ignimbrite there is actually has the same oxygen isotopes and the same very similar composition to the Smith Rock tuff. And so because of the O18 and oxygen isotopes and helium isotopes, these two things have recently been put together as the same thing. So let's take a look at the Columbia River basalts. This is Joseph Canyon in Northeast Oregon. Let's see, you guys will be here until 9 o'clock tonight, right? Carrie's laughing.
I was
Okay. Anyway, here's the
commenting to
Columbia River
folks that
basalts.
we may go over a bit and they're welcome to leave, but some of us are going to hang on forever as long as you're talking, Ellen. So not a problem.
So at any rate, so here's 20 to 30 million years, hydrated mantle being sort of reformatted by the rise of that plume. If we look at the Columbia River basalts, you'll find that they erupted basically through dikes. These are dikes in cornucopia. So is this. The Wallowa Mountains seem to have a disproportionate concentration of basalt dikes of primarily Imnaha and Grand Ronde, but also Saddle Mountain. And so for some reason, this hotspot basically found its way into the Wallowas from where it had from far to the south. And the reason for that is not entirely clear, but Vic Campbell and others can think that as North America moved to the west, see if I've got as North America moved to the west, it basically, the deeper continental material sort of reached down into hotspot magma chambers and shoved or condensed them. And so some of that material moved to the north. So you can see his diagram here where you're actually moving. Where did my arrow go? Oh, well, and so you can see that the darker brown basically moves up to the Chief Joseph Dike Swarm, the Monument Dike Swarm, and gets squeezed also down further into Nevada by the encroachment of the deeper continental material onto this hotspots plume. This is the McDermott caldera, and this is supposedly where the hotspot first arose. It's about 17 million years old, but so are a lot of the Columbia River basalts. And so, it's quite evident that the McDermott caldera was not the first place that the Columbia River basalts showed up. So we're going to we have the Columbia River basalts being composed by this hotspot. We're going to take a look at some of the other products of the hotspot and how they compare. First of all, I want to put this diagram up that basically compares the ages of all of what are now called the Columbia River rhyolites over on the right-hand side with the Columbia River basalts. And actually, if we put McDermott caldera and the high rock calderas on this would extend down to about 17 million years. And so you'd see that the rhyolites, discriminated against rhyolites, are being erupted at virtually the same time that the Columbia River basalts are. So these are the Strawberry Mountains. They were considered to be, they're calc-alkaline. They're actually atacites. They're a product of melting of that hydrated mantle as the hotspot kind of burns through the Farallon plate. They're, as I said, primarily andesites, but there are also dacites, rhyolites, and a few basalts in here. So they're not all that different from what you would find in the calderas along the Snake River Plain. This is a picture of the wall and that cirque. This shows about 200 feet of that wall. So it's quite an impressive structure. This is a rhyolite on Dooley Mountain in Oregon, just south of Baker City. It also has been fingered as a Yellowstone hotspot product, a product basically caused by melting of overlying crust by by the Columbia River basalt magmas or Yellowstone hotspot magmas. This is the Dinner Creek Tuff, which erupted from, you see where the red oval is there. That's kind of the area where the Dinner Creek Tuff has a number of calderas that erupted it in several different episodes. Anyway, there's several different calderas in this area that basically are produced this tuff that covered over about 8,000 square miles. We find the Dinner Creek Tuff, even though it was erupted south, basically of way south of Baker City, we have thick accumulations of it here in Halfway. It goes all the way up to La Grande and all the way up to Elgin and into Idaho in some places. This is Pride's Castle in the Owahis, which are also a Yellowstone hotspot product. You can see that this is a bimodal group of rocks. So you have rhyolitic tuffs on the bottom. Then you've got basalt, rhyolite, basalt, rhyolite. This is in Leslie Gulch. It's a dike that basically came up through the Mahogany Mountain caldera as tuffs were erupting. It's similar basically to the dikes at Smith Rock in terms of its composition, in terms of its function. And then just briefly, there's also the La Grande Hawaii eruptive axis, where Mark Ferns and Jason McClary, who've mapped much of this, consider this to be an area. So here's Elgin and La Grande. You can't see if I'm pointing at my screen, can you? So here's Elgin.
I can see your arrow.
Jordan Valley, Pendleton is over here, John Day is over here. You guys are way over here in Portland. So you can see basically this La Grande Hawaii axis. And this is a place where potentially some Yellowstone hotspot lavas have been sequestered. And as the continent continues to move, they get squeezed up. And so you end up with the Dinner Creek Tuff erupting actually at 17 million years, but then you get later products that include things like the Powder River volcanics, which are here. This actually the top right photograph is Dinner Creek Tuff near Richland, Oregon. It's actually a welded tuff at that point. These are Powder River volcanics. They're andesites at Catherine Creek State Park over by La Grande. Also fingered as relatives of the Yellowstone hotspots were Keating volcanics and Keating Tuff near Baker City. And finally, Cinder Butte, which is south of downtown metropolitan Hereford and northwest of Ontario. It's dated at about 800,000 years and is conceivably the last emanation of volcanics in Oregon that can be kind of pointed to as Yellowstone hotspot. So we have a tremendous amount of geography and topography, including the Columbia River basalts, including the John Day Formation, including potentially part of the Clarno Formation, including the Owahis, including some of the deformation and rock formations in Washington that we can thank the Yellowstone hotspot for. And so this is what things look like today with the hotspot producing Yellowstone and, thinking about its next move and these, dikes and materials that are left over here in Northeast Oregon and all the way across Oregon, in fact. So again, these are two things that erupted simultaneously, crafted a tremendous amount of Oregon and Washington's landscape, and I will quit there.
Ellen, thank you.
No.
Thank you so much. That was just wonderful. And your photographs, oh my gosh, they are just so beautiful.
Yeah. Oh, thank you.
Oh, your photography. Wow. You had a question right off the bat. Yes, lots of kudos and thanks here.
Something I noticed, and I've thought about a little bit, kind of in the past. I'm one of the few people in my lab group that is not studying Columbia River basalts or rhyolites. So I'm working in the Cascades. But it seems like the footprint kind of the Yellowstone hotspot products was a lot wider in the past because you've got like basically the trace of the Columbia River basalts all throughout Oregon and Washington, and then it seems like it's got a lot more constrained. Is that correct?
Yeah, I think that's a great question. So if you think about what the hotspot was what was going over the hotspot, basically, particularly as it was going through Eastern Oregon. We're a landscape that's composed primarily, our basement is accreted terrains.
Yes.
And those accreted terrains have, multiple terrain boundaries. They have multiple faults. They have multiple fractures in them. And so I think that Camp thinks, a lot of us think that one of the reasons that you have so many other, this extension of basalts over here and rhyolites over there is that plume could find many different pathways to the surface. The other thing is that if in fact North America's much deeper crust was impinging on that plume, then not only do you have multiple pathways to the surface, but you also have maybe some pressure. It's kind of like one of those water bottles that you get that you can squeeze and it filters the water for you. It's basically that's one explanation. But like all paradigms, this is one that's new. And it's one that people need to, our science has started since about 2014 or so, started to really dig into these questions like the one you just asked. So we need a lot more data to be able to, stop waving our arms and say, okay, so this is actually what happens. I mean, when you see Martin Streck, you might just ask him what his idea is about this, because I'm sure he has some ideas. But actually, Martin is probably the top cheerleader for the rhyolites.
Oh, for sure. Yeah, he's my advisor. I've heard quite a bit.
Yeah.
That's makes a lot of sense though what you're talking about with the multiple pathways, just because it's a like conglomerate of accreted terrains.
Yeah,
So that does make a lot of sense. And then the transition into the cratonic crust, I
mhm.
think would constrain that a lot more.
Right. And yeah, when it goes into the cratonic crust, it doesn't have as many options.
Yeah, that makes a lot of
You know,
sense.
it's like
Thank
there's
you.
a freeway and it makes its path through the crust, and then it's like, oh man, I'm so glad I got to the surface finally. As opposed to having all these sort of anastomosing channels that it can go through.
For sure. Thank you.
Yeah.
Which actually leads us into this next question. How does the clockwise rotation of Oregon around 20 million years fit into this as well?
It does. It does. Yeah. So, the pathway, the most accepted pathway, that's a great question too. The most accepted pathway of the hotspot is, kind of along the southern border of Oregon. At least that's what Vic Camp and others have postulated. And so if you take that, and you're looking at what was at 30 million years ago, then you can rotate what becomes the Crooked River caldera to the north. You can basically move Silesia up to the north, so it's now, forming things in Washington. So yeah, I think the rotation basically had a lot to do with the current location of some things, but less and less the farther east you go.
Because you're hitting the solid stuff as opposed to the broken, in
Yeah,
theory,
I mean,
broken up.
yeah, I mean, if you look at the pathway and look at where the hotspot track of at 20 million years or 17 million years, it's closer to where the Columbia River basalts began to erupt, but it's not right there. So yeah, there's obviously some squidging going on with the hotspot, and some opportunistic saying, I think I can make it up through this pathway, and then I can make it up through this pathway. But there are just so many questions, like, why did it choose the Wallowas, which, there's a big blob of granitic rocks. Why did it choose that as a spot to, melt off the root of the eclogite root of the Wallowas at, around 15 million years, 14.5 million years, so that was delaminated and fell away, and then you ended up with the Wallowas beginning to rise. So I mean, at one point, was it 12 million years? There was a paper that just came out that I skimmed through before this talk, so I'm not remembering all the dates correctly, but but the Wallowas were 1.5 kilometers higher than they are now
Wow.
at like 8 million years ago.
Oh my gosh.
Yeah, the world's a funny place. It keeps moving. We think we're stationary, but if we're actually moving at 1 billion miles an hour, if you consider that the Earth is rotating and it's going around the sun, and the whole thing is the whole solar system is moving, and the galaxy is moving, and I'm just sitting here.
Wanna
Do
unmute
they
Matt?
use chemical analysis with the different areas to see if there's a relationship between some of these rhyolites or basalts, or are the eruptions too far apart by millions of years that it's
No,
hard to
there's
detect
there's
that?
definitely isotopic signatures in these rocks, trace element signatures. So, yeah, it's basically, kind of nailed down with geochemistry.
Thank you.
Yeah, I
Yeah.
think that's how a lot of the studies have been done is through geochemical analyses, trace elements, isotopes, whatnot.
The next question here is the trace of the hotspot is showing entering North America about Cape Mendocino. How does it affect volcanism much further north?
That's another great question. I think basically, there's a question about how did it affect the Western Cascades, for example.
Mhm.
And as far as we can see, there's not much in the way of hotspot activity in the Western Cascades, but then no one's really looked. No one's really gone in there with their hammer and tongs and taken samples and hauled them back to the laboratory and said, I think maybe this particular volcano is affected by the passage of a hotspot underneath. Maybe there's something going on here. So we don't know if there's any relationship between the hotspot and the Cascades, the Western Cascades.
Okay, so, and this is something that I remember hearing about in school. Please talk about the Olympic Wallowa liniment. Is there any relationship there?
Oh, that's another great question. But there's lots of tectonic. Well, the Olympic Wallowa liniment is basically, you've got the Wallowas on one end, and I think it's certainly not related to the Yellowstone hotspot, as far as I can see.
No, but there's something going on
There's something going on. And, if you look at lineaments, if you look at the Alvord Fault on the east side of Steens, okay, that actually lines up perfectly with Hell's Canyon.
Mhm.
So, that's something I've been wondering about for a long time is, but I have no data. I just look at the map and say, wow, isn't that strange? The same way with the owl. I think we all look at things and say, wow, that's really weird. But hopefully someday someone will come up with owl.
So Alyssa, Cameron, and your compatriots that are here listening, there's more out there for you to study. There's a lot of puzzles, and that's our, that gets away from the Cascades. This is actually more of that Eastern Oregon, Eastern Washington that aren't quite so shiny and pretty as the Cascades. I'm just
Oh, but
saying,
they're
just
more
saying.
open. They're much more open. There's a lot more to see out here. We have rattlesnakes.
And scorpions.
Oh
Yeah.
yeah.
Well, you may have scorpions down there. We ain't got no scorpions up here in the Wallowas.
One thing I
Okay.
will say is it seems like there's a lot more people working in Eastern Oregon than in the Cascades. I'll say that. But
Oh,
there's
well,
no shortage of questions in either place though. So
no, there's not. And I think you'll find that's one of the things that developing paradigms do. It's like, wow, I can get funding to study this thing, but we know all about the Cascades, so why would I go over there? Because I can't get funding to do it. Actually, nobody can get funding anymore for anything at this point. But it's, so the thing about a new idea, it's like Harlan Brett's and the floods, right? In 1923, he wrote this wonderful paper, and nobody believed him. Doug Pyle in 1980 came up with this grand idea, and he couldn't put it in his thesis because his Bob Duncan believed him, but his geology, Bob was an oceanographer, and Doug's geology committee members were like, oh no, that doesn't make any sense. It's a huge geosyncline. The anyway, so yeah, there's so this new paradigm means that we're going to be asking lots of new questions to test it, to support it, to pull it apart. I mean, there's still people who think that the mantle plume that it's not a mantle plume, that the Snake River Plain is a long fissure, some sort of a fault thing that the hotspot was able to go up through, as opposed to, or maybe just pulled apart and mantle oozed up there. So there are non-believers, and if actually, I'll do a quick advertisement here. All right, so this is called Living with Thunder. It's a brand new book that I wrote, just published by Oregon State University, and it has a lot more details in it about the Yellowstone hotspot than I've been able to blather about today,
Whoa,
along with a
wonderful.
whole bunch of other things. So It's
Whew.
available on Amazon, and I'll be talking about it at Powell's on November 4th. And anyway, thank you all very much for listening.
Ellen, thank you. Thank you so much. I know we went over, but I think it was all worth it because paradigms, they change, and this is all new stuff, and it's just fun to learn about our geology and how that story keeps changing.